Northwestern University.
Yes.
She's going to talk about complex dynamics and elliptic curves.
Thank you. And thanks for the invitation. It's really a pleasure to be here and to speak here. Complex dynamics and elliptic curves. So over the last number of years, I've been thinking about connections between complex dynamical systems and number theory, or questions in arithmetic geometry, sort of questions that were really about dynamics but inspired from statements and results on the arithmetic side. And then very recently, we realized, together with various co-authors, that we could sort of push back and go the other way and even try to answer some of the questions from arithmetic geometry using these complex dynamics methods. And so I want to tell you a little bit about that now, but I'm tired. It's the end of the day. I'll try not to do anything technical. I want to emphasize the sort of soft ingredients, but really the complex dynamics pieces and not the number theory side. So maybe I'll just begin by saying, so what is the setting? I'm interested in studying families, or what we call holomorphic families of rational maps. Is this big enough? Yeah, can you see? Okay. So f, say, sub t. So t is my parameter. And I'll think of t as a complex parameter, so it's living in some Riemann surface. Interested in various dynamical features and stability of such families. There are two main examples that I'd like you to have in mind throughout this talk. So I'm going to just write them down. Well, I guess the main example would be, or the basic example would be, the quadratic polynomials to keep in mind. So I'm using t instead of c here, but again, t now lives in the complex plane. And the other example is, well, that I'll write down, will be a family of degree 4 lattice maps. So the particular formula I'd like to think about will be the following. Minus z squared minus t squared over 4z, z minus 1, z minus t. Is that correct? Yes. Okay, so this is just and t here now is living in the triply punctured sphere c minus 0, 1, so that it has degree 4. Okay, so this is sort of the basic setting. So let me go ahead and introduce some notation and then tell you a little bit about what the number theory statements are, or some of the classical statements that I want to describe from a complex dynamics point of view. So the setting to think about here is to, let's say I'm going to let X now be a compact Riemann surface. And I'm interested in the function field of X. So K here will represent, so C of X, the function field of X. So this is just the meromorphic functions on X. It's just the field of meromorphic functions. On X. Okay. And so a family of this sort is nothing more than a rational function defined over this field. So a family here will be a rational function with coefficients in the field K. So a rational function in K, where let's say I assume that the degree of f is at least 2. So this is corresponding to one of our holomorphic families of dynamical systems. So this is really ft going from, of course, now this P1 is over the complex number, so this is just our Riemann sphere. But now, in order to sort of make the change of language, I just want to emphasize that notice here, of course, this is the parameter space is not compact. If this is non-trivial in any way, the parameter space won't be compact. It has to have some punctures. So here, really, the typical setting would be I have this holomorphic family of rational maps as long as I puncture my x. So t here will generally live in some, maybe I'll write it down below. So the parameter will be in some punctured Riemann surface, and maybe I'll use this notation x star. So this is going to be, say, x minus some finite set, where, so for all the t's here, so that the degree as a complex rational function is constant, is equal to d for all t in x star. Okay, so x star just means that I'm puncturing the parameter space. So that, here, of course, x is p1 in both of these examples, or the Riemann sphere in both of these examples. Of course, I have to remove infinity for this particular family. And here I have to remove t equals 0, 1, and infinity because it will have drop in degree. Okay? So this is just the language I want to use. So this is really the same thing. All I've done is introduce new language for the same kind of thing. And in fact, in some sense, what I'm talking about is really just playing around with language, going back and forth between statements that one can make in an algebraic context and statements that one can make in a complex analytic context, and really just play these against each other and see how far you can get. Okay? All right, so let me now mention a classical result from number theory, namely the Mordell, what's now called the Mordell-Weil theorem about elliptic curves. Okay, so here's the theorem due to Mordell and independently Weil in the 1920s. Well, I guess they contributed different ingredients. Mordell proved this theorem over the field of rational numbers, Weil extending to arbitrary number fields. So what's the statement? So let E be an elliptic curve defined over a number field. I'll remind you what that is in a moment. Just a second. An elliptic curve over a number field. Maybe I should say it here first. So let K be a number field. So rather than the function field that I've written there, which I'll come back to in a moment, let K now be a number field. Okay. Just remember, that just means a finite extension of the rationals. So let E be an elliptic curve over K. Actually, well, I'll just remind you now. So of course, what does this mean? So just think the following presentation. E in, say, Weierstrass form, E can be expressed in the following way. It's just the solution to the following, let me do it this way, actually, in Weierstrass form. Cubic equation. So think of this as a subset of P2, where A and B, so to be defined over K, just means that the coefficients are in the field K. So here A and B are elements of your given number field. OK, I wrote think. I can erase that. So that's just what it is. And so what's the statement of the theorem? The theorem is that if you look at the rational points in E, that they form a finitely generated group. OK, so the rational points which is generally denoted this way. So again, rational points just means the points x, y, whose entries are actually in the given field. So defined over the field K. So the rational points form are finitely generated. So a finitely generated subgroup. Okay. So that's the theorem. All right.
What's the group one here?
So, sorry, well, addition, but it doesn't have a particularly nice presentation in these coordinates, but it's just the usual addition formula on an elliptic curve, which can be expressed geometrically. If you've seen the geometric picture, but if you plot this thing over R, and let's say the solution looks something like this, and I don't remember now how does the additive group law work. If you want to add this point to this point, you draw the line between them because it's cubic. You hit in a third point, and then the negative of that point is actually the sum of those 2 points. And that's what gives the addition law. The point at infinity is the origin in this group structure. Yeah. But I mean, to write that down in a formula, I don't remember how you write that down. So Okay, so all right, so this is a classical result. Proof is well known to number theory students, and so I guess there's one piece of it that I want to emphasize, which is a consequence. So this is some finitely generated abelian group. So there's a torsion piece, and then a finite rank infinite piece. So in particular, the set of torsion points is finite. So here's this piece that I want to emphasize. In particular, if you look at the set of points on this elliptic curve of rational points, which are torsion, this is a finite set. Okay? Because the group is finitely generated, so the torsion part certainly has to be finite. Remember what torsion means. This just means you add it to itself some number of times, and you get 0. So there exists some n positive integer, so n times p is just the 0 in the group law. Okay, so now, so this is this classical result from the 1920s, and actually, what did I want to say? I want to remember what I want to say. Oh yeah, just to point out that, of course, if you do this, oh, I see. If you think of this as a complex, I mean, as a Riemann surface, if this is, say, P2 over C, and you look at the complex solutions, we know that this is a torus. And of course, the torsion points are in fact dense. If you take all of the torsion points, say, over the algebraic closure of K, or over the complex numbers, this is an infinite set, a dense set. And in fact, just recall, of course, if you present E over C, you can think of it as the quotient of the complex plane by a lattice. And we know that we have this picture, this lattice picture in the complex plane, where let's say this is 0, this is 1, this is my other generator of the lattice tau. And we know exactly what the torsion points are. They're just the rational, rational multiples of these generators summed together. Okay? And so certainly the torsion points are dense in here. Torsion points are dense here. Okay, so what this statement is saying, if you just look at the rational points, there are only finitely many defined over that given number field. Okay. So then one could ask, what happens if you change number field to function field? You should expect a similar kind of statement. But it turns out that just writing the exact same statement and let K, if you let K now be the kind of function field that I'm interested in, let's say the meromorphic functions on my Riemann surface X, then this statement is false as I've written it. So it doesn't quite hold. So this statement is false. And I'd like to illustrate what goes wrong with a sort of simple or a silly kind of counterexample over here on this board. So just to illustrate, what goes wrong. So of course, what does it mean if you think of an elliptic curve over a function field? So these coefficients here, a and b, are now meromorphic functions on x. So they depend on some parameter t. So you can think of your elliptic curve over the function field as now some holomorphic family of elliptic curves, so parameterized by t in your base x, or in other words, the picture you should have in mind, is of this complex surface, the bundle where the fibers are the elliptic curves and the base is x. So you should picture your Riemann surface x down in the base, and then your fibers over some point t is some elliptic curve t. Okay, so you have some surface here. So this elliptic curve or a function field you can picture, of course, in this way. And you have this projection down to x from the fiber down to the point. So what is a rational point in this case? It's just a section of this projection. So if I take, a rational point corresponds here to just a section of this, I don't know, let's say this is a boldface E to represent thinking of it as a complex surface. So this is just a section now of this surface over x. Okay? This is just formal from the definitions. Okay, so what goes wrong? Why would this collection of rational points perhaps not be finitely generated? So if you take just a sort of silly example, suppose this surface is just the product surface, x crossed with some given elliptic curve E naught. So all of these fibers are exactly the same. So this is just a product surface, which is of course projecting down to x. So as if that were the case, well, we know that the torsion points on any complex elliptic curve, well, there are infinitely many of them. So take one of them, let's say one right here. Suppose that's torsion on a fiber. Well, of course, then I can cook up a section. I can just take the horizontal slice through that point. And I can do it for all infinitely many of these torsion points. So it's fairly easy to see that in this trivial case, or more generally what's called the isotrivial elliptic curve, which means under base change, under isomorphism, you can put it into this picture. Then what happens is that in this trivial case, what you get are there are sort of infinitely many. So in this case, there are infinitely many torsion points, rational torsion points, sorry. I want to emphasize the fact that they're all rational. Again, so rational just meaning that they're defined over the given field. Okay? But it turns out that's the only problem. Being, at least up to change of coordinates, up to base change, being trivial in this way, so really just means the complex structure of the torus is not changing. And if that's, as long as the complex structure is varying, then you get the corresponding Mordell-Weil theorem. So let me just write that down. So the theorem here, which is now, most of the proof goes through exactly the same. So I guess I can attribute this now to, say, the ingredients due to Mordell, due to Weil. Maybe it's often in the literature attributed to Lang and Neron in some 1959 article, although that was, of course, the emphasis is abelian varieties instead of just elliptic curves. And I'm not even sure it's quite stated there with proof. Really, I would say more the ideas of Tate from the 60s, et cetera. OK, but what's the statement is exactly the Mordell-Weil theorem for function fields such as this that I'm looking at, but with an extra hypothesis that E not be isotrivial. Okay, so the hypothesis says, suppose E is now an elliptic curve over, I'm just dealing with this kind of field here, this particular function field of my Riemann surface X, which is not what's called isotrivial, then the same conclusion. The group of rational points is finitely generated. Okay, you get the same conclusion. Okay, so and again, isotrivial just means that the complex structure of the tori is not varying. All right. Oh, okay. All right, so I guess what I want to do fairly quickly now, if possible, is to give a complex dynamics proof of the missing piece, to go from, say, the classical argument to the piece here. So that, in fact, really the only piece that you don't get automatically in this case is the finiteness of the torsion points. So what you need to prove in order to get this theorem, from following all the arguments for the Mordell-Weil theorem for the number theory case, the number field case, is to prove, well, exactly this, that the set of torsion points is finite, that the set of rational torsion points is finite. Okay? So I'd like to present a complex dynamics proof. Yeah.
Everything that's approved?
Well, there's a lot of other stuff that one needs to sort of argue why what I'm about to write down would be enough, which I'm not going to say. But actually, some of it is presented in an article of Matt Baker that appeared in 2008. So I need to prove, maybe I should mention his name. So he was looking at, well, I'll get to the statement later, but studying families, rational functions defined over function fields. And in an appendix of an article from 2008, he goes through and explains how you can recover the statement that I've written completely from just knowing this thing about the function field. I mean, about the torsion points. So complex dynamics proof. And in fact, I don't want to give the whole argument. Let me just. No. I'm repackaging it because I just want to show you for one example, actually. So in fact, let me give the argument for one example, and then I'll explain, of course, how heights come in after. No, I mean, there's nothing fancy about the heights. It's just I want to do it concretely. So I'll just do this for one example. And the general case is similar in spirit, but certainly there has to be a little bit more work to go into it, which in fact involves some general statements about certain canonical height functions. So let me just do it for one example, namely E. So K, let's say X will be the Riemann sphere, so P1. And so what is the field then? Field is just the field of rational functions in a parameter T. And I'll do this for the Legendre elliptic curve, which is the following. X times x minus 1. So it's not written quite in Weierstrass form here. So this is smooth as long as t is not equal to 0, 1, or infinity. This is what's called the Legendre family of elliptic curves. And the argument that I want to give is it's just a computation, actually. And it's a computation that appears in an article together with Xiaoguang Wang, who's here. There he is. And my former student, Hesi Yi, that appeared, or I guess hasn't yet appeared. But anyways, this computation I want to show you appears there. And so what does one need to show? OK, what did I want to say? Well, I guess the first observation, what does this have to do with dynamics, which is why I kept this one up here on the board, is very well known to the complex dynamics community, even the number theory community, that if you take an elliptic curve over any field now, take an elliptic curve, and in this case, this projection will just be, it projects with degree 2 down to P1 just by identifying a point with its additive inverse. So glue P to negative P, and that gives you this projection. And then any endomorphism upstairs, and in particular, we can take the multiplication by 2 endomorphism upstairs on the elliptic curve, descends to a rational function, f, downstairs. Okay? And if you take multiplication by 2 on that elliptic curve, and if you choose coordinates so that, I'll just write it here. If you choose coordinates so that the projection is just x comma y here, of course, that's what this is, but choosing the coordinates downstairs, so I just have the x coordinate downstairs, that's exactly multiplication by 2. So this ft, as many people here know, is just the formula for multiplication by 2 on that Legendre elliptic curve, but as seen down here on P1. Okay? And why is this useful? Just the very basic observation is that if P upstairs is torsion, then its projection downstairs, I don't know, I guess we can call this curly P for the P function, then its projection downstairs is pre-periodic for F. Okay. So therefore, if I want to say something about torsion points on the elliptic curve, I can study dynamics of this particular map downstairs on P1. Okay, so that's really just the basic observation. So then what do we do to show finiteness? Well, you can just, in this particular example, you can just do some computations. So I just want to show you what that might look like. So the first thing to note for this particular example, Well, there are a few pre-periodic points, rational pre-periodic points, that are easy to write down. So maybe I should say, what is a rational point here? So now I'm down on P1. So what is a rational point on P1? Okay, so remember K is my function field here, which is just rational functions. A rational point is just itself a rational function, or identically infinity. So this is just, P is itself a rational point, or maybe it's the constant function, infinity. So P itself is a rational function in the parameter now. T is my parameter, remember. Okay, so if you let P, for example, be identically equal to 0, or identically equal to 1, or the function T, or infinity. So here are 4 points, rational points on P1, rational in T, that we can see immediately are pre-periodic. So we know this is exactly the post-critical set of this map. Infinity is fixed, and 0 and 1 and T are sent to infinity. And anyways, this is precisely the 4 post-critical sets for this map. So we know that for those 4 points, they are pre-periodic. Thus, they are descending from torsion points. Okay, so F for all of these, if you look at Ft evaluated at P of t, this will be identically equal to infinity. Infinity is fixed. And infinity is fixed. And so these are pre-periodic. So these are pre-periodic. And then what happens for every other point is just a little computational lemma, which appears in this, where did I mention it? Yeah, appears in this article, that is just to observe that in this case, as long as P is not one of those 4 points, so for any other rational function, so if P is not equal to 0 or 1 or T or infinity, then I want to say that it's not pre-periodic. So what happens? Then in this particular case, if you compute the degree of the image, P is a rational function in T. I'm plugging it in for Z over there, so I get another rational function in T. And I can compute its degree as a rational function in T. And one can show, with not very much work, but I'm just going to skip it for time purposes, that this is always at least 2, no matter what P is, as long as it's not one of those 4 points. No matter what it is, the degree becomes at least 2. And furthermore, once you get past that first iterate, all further iterates have exponentially growing degrees. I don't know, let's call this, d sub 1 of P, so times d sub 1 of P. So this is in particular going off to infinity as n goes to infinity. Okay? These are the iterates of P under F. The degrees are growing as functions of the parameter, so they cannot be pre-periodic. If they were pre-periodic, this list of functions would be finite. Okay? So if the degrees are growing to infinity, certainly it's not finite. So all of these, so this is just a little lemma, but the conclusion of this computation, I guess I can erase this, is that, I don't know, I'm going to do OK with time. So the conclusion is just that the set of all rational points on P1, which are pre-periodic for this particular family F, for this particular F, this particular lattice map F, is precisely this set, 0, 1, T, and infinity. Now, if you want to look at the torsion points up on the elliptic curve, those that are rational all project to such points. So the size of this is no bigger than 4. But each of them, in fact, lifts to a rational point upstairs on the elliptic curve, because if you just set x to be equal to 0, y is 0. If you set x equal to 1, y is 0. If you set x equal to t, y is 0. And infinity is infinity. So the point being that each one of those is, in fact, also rational upstairs. In fact, this is just the 2 torsion group. This is just the 2 torsion points on E. And this has cardinality 4. There are 4 of them.
Here, are they somehow easier to see working with a Lopez map than directly by multiplying by 2 upstairs?
Yeah, I don't know. I guess I didn't try. So in fact, this is a lemma that we use for something completely different. So, but I think, no, I think it's, I'm not sure that, I mean, what does it mean to multiply? So what is multiplication by 2 upstairs? Multiplication by 2 is this function, right? Exactly. So, I mean, it's the same thing. It's just that the way that we actually compute this degree growth, it's convenient. I mean, yeah, ultimately it's the same thing. So just to be able to get this induction going and to get the degree growth going, it's convenient for us to know that this is a rational function on P1 and just to exploit. I mean, it's just a computation. It's just a computation.
Could you say something more about that basic step, that P is torsion if known if the image is pre-periodic?
Yeah, here, yes, absolutely. So here, just notice what's happening here. So if it's true that, so if you look at the entire set, so let me go in one direction. So if you look at the entire set of P plus P and 3 times P, etc. So being torsion means that's finite. Okay? So in particular, there's a step here in between that I didn't write down explicitly. Being torsion upstairs is the same thing as being pre-periodic for multiplication by 2 upstairs. Because if this entire list is finite, then certainly just taking the powers of 2 is going to be finite. So that's why it's pre-periodic downstairs. Okay? And the converse is exactly the same, because it's just multiplication by 2. Knowing pre-periodic downstairs tells me exactly that the list here of the powers of 2 times P is finite. So there must be a relation of the form 2 to the m times P is equal to 2 to the k times P. So therefore, I get torsion. Does that answer the question? Okay, so it's just, there was this in-between statement that I guess I didn't write down. It's just knowing that torsion is just pre-periodic upstairs on the elliptic curve. I mean, the quotient is just identifying P and minus P. So certainly one is torsion if and only if the other is torsion. So that's why it only depends on what happens to the x-coordinate. So fundamentally, this is just a computation. Okay? But it turns out, so I should say, I mean, this is not new information either, of course. Like the fact that there are only 4 torsion points in this family was certainly first computed around 1900. This is well known. This is not new information. And in fact, yeah, I mean, but I don't know what the sort of the way that it would be looked at. But how to do it in general. So of course, this is for this very, very particular family. If you want to know for an arbitrary elliptic curve, one can't rely on the explicit formula. And it turns out, of course, that the same kind of argument, but just using complex analysis, gives the finiteness in general. And so let me just say a couple words about what kind of things would go into a more general statement. So what am I really looking at? In fact, the general statement doesn't use anything about coming from an elliptic curve. The family does not have to be lattice to talk about, to get this kind of finiteness, or rather, I should say, finiteness of the set of pre-periodic points, which I will write down in a moment formally. But basically, just to emphasize what I'm actually interested in is the following. What I'm really looking at is any rational function with coefficients in my given function field. And I want to assume, well, any rational function. I want to assume the degree is at least 2 so that I have some interesting dynamics. And I want to look at rational points. So remember that, I've already written. So a rational point, maybe I should emphasize here. A rational point on P1 before I emphasized that it was therefore just a rational function of the parameter t. So what does that mean? In other words, this is the same thing as a holomorphic map from my parameter space to P1. So these are my rational points. Of course, extending to, if I pass to a finite extension of this field, that would correspond to a branched cover of X. But I'm going to keep this, I just want to talk about rational points to keep it simple. And what I'm really looking at is the following. So I'm looking at here, so I already said look, okay, is the following collection of maps, the iterates of P as viewed as maps from X to P1. So what I'm interested in are the maps of parameter T going to the iterates F sub T and of P of T. So this is a sequence of holomorphic maps from X to P1. So this is all iterates n greater than or equal to 1. And what is this argument, this lemma, just for this one special case doing? It's computing the degrees. Okay? So what I'm really interested in general, is looking at these maps for various rational points P at the degree growth of these things. So what we're really interested in is so these are maps, holomorphic, these are branched covers basically, from X to P1, and I'm interested in the degrees of these branched covers. So I want to compute, let's say I call this, I don't know, let's suppose this were some holomorphic map Gn, and I'm interested then in the degree of Gn as n goes to infinity. What is the degree growth of these things? And this is the height that you alluded to, Adam. So let me say, actually, I want to spend a moment saying, just putting this in context, in dynamical context. I mean, this is not, there's nothing, I haven't really said anything new. I just, but in a dynamical context, it's a very common thing to look at this sequence of functions when P is a critical point. So if you're handed a family of rational functions, it's very common to look at exactly this, and I'll say why it's common, this exact sequence, exactly this sequence of functions when P is parameterizing a critical point. Because then the behavior of this sequence of functions is detecting stability in the family, dynamical stability. Okay, so let me just say a few comments here. So if P, the point parameterizes a critical point, of this family Ft, then what? So, oh, I didn't define stability. Sorry, let me give a quick definition, and then I'll say what I was going to say. Any rational function with coefficients, here you are, with coefficients in this that are meromorphic functions on a Riemann surface X. Yeah, any F. It's not necessarily a lattice map. Okay. And in this setting, if F is such a function and P is a rational point, I want to say that this pair is stable. There's just a definition here. Is stable if, oh, maybe I should say where, on some open set U inside X, except that, well, sure, I'll just say U inside X. If this sequence of functions is forming a normal family. So if that sequence of functions, T, the iterates, is normal. Okay, now let me put this up. Finish what I was going to say. Okay, so this is just a definition. I'm just looking at this particular sequence of functions, and if it behaves well, on U, yes, on U. Yeah. Yes, if it's forming a normal family on U. Okay? And I just want to emphasize why this is actually a familiar notion in complex dynamics. Okay, so if P happens to parameterize a critical point, then this is exactly how stability is defined or used in the context of holomorphic dynamics here. So what is the statement? So this is a theorem which, well, maybe I'll just write it this way. So independently, I guess, of Magnier, Sod, and Sullivan, and Lyubich, published in, I guess, 1983. By the way, Misha, where's Misha? I only recently learned about this particular article of yours from 1983, so I have to apologize publicly for not having referenced it for years. Okay, so including my very first talk while a graduate student here visiting Stony Brook, giving a lecture in front about stability. Misha was in the audience. Dennis Sullivan was also in the audience, and I didn't even know. I had no idea. And he's so polite. He never corrected me. Okay, sorry. Okay, so just to say, all right. So what is the statement? The statement being that if you know that all of the critical points, so suppose I parameterize all the critical points for all critical points C of F. So if they're all stable in this sense on some neighborhood U inside your parameter space X, this is equivalent to dynamical stability in this classical setting that the maps are structurally stable, at least when restricted to their Julia sets. Okay. So this is that the maps, when restricted to their Julia sets, are all are topologically conjugate in small neighborhoods, so structurally stable. Okay, so this is exactly this notion of stability which plays a role in structural stability. And let me mention two more theorems related to stability in the critical point case before I state a theorem, which is, I guess, one of the objectives of this talk. I want to leave that up, actually. Let me erase this. I have so many boards, and I was getting confused about which ones to use. So just a couple more things just as background regarding this notion of stability. So one more result. Okay? All right. One more result I want to mention, which is due to McMullen, published in 1987, in fact, related to the theme of Dirk's talk in the previous lecture. As he was studying root finding algorithms, one of the things that he proved at the time was a rigidity statement, which is related to everything that I've written up here on the board. So let me just formulate the statement in this language. He proved that if you start with one of these rational functions over a function field of, as usual, of degree at least 2, and if I assume that it's not trivial or not isotrivial, to use this language, so not isotrivial. I have not defined that in the context of rational functions yet. This just means that they're not, so if you think of this as a family, actually maybe I should write this out. So again, so this is a family of dynamical systems, but it's not for all t in the compact Riemann surface. Remember, as a family, I have to puncture my x. And this plays a role in, and it's related, of course, to the hypothesis of this theorem. So this was the punctured Riemann surface x, so that where the punctures were just chosen so that the degree is constant, say d, for all t in this punctured Riemann surface. Okay, and isotrivial means that they're all conformally the same. They're all conformally conjugate. That's isotrivial. They're all conformally conjugate. If you assume it's not, so they're varying in some non-trivial way, then the statement is the following. The statement is that they're stable, they're structurally stable, or I'm going to write it in terms of the critical points, that these are stable on the entire parameter space for all critical points C, if and only if what? If and only if each of those critical points is actually pre-periodic throughout the family. So if and only if each critical point is pre-periodic. Again, this is throughout the entire family. So for all T, these critical points are persistently pre-periodic. So this is a rigidity statement about stable families. If it's stable on the entire domain, the entire punctured Riemann surface, then these critical points actually all have finite orbit. And then he appealed to Thurston's work, Thurston's rigidity statement, to say, but then we know exactly what these maps are. They have to be lattice maps. In other words, they have to be descending from an endomorphism of an elliptic curve. So because of the non-isotriviality, he then cites Thurston's work, which says, well, this is equivalent to saying that this family, or I should write it this way, there exists a diagram of the following sort and some endomorphism on the elliptic curve, sorry, not F, P1, so that F is a quotient of an endomorphism on a non-isotrivial elliptic curve, necessarily. So just to put this sort of language into the, or put this theorem into the context of this language. Okay, so the theorem that I want to state, yeah?
You have to think when you write FC is stable for critical point C, you have to think that we are able to parameterize the critical points.
Yeah, so the way I'm formulating it, I'm assuming that, say, my critical points are parameterized. But of course, I don't really have to formulate it that way, and he doesn't formulate it that way. In fact, one can assume that I pass to some branched cover of the parameter space, parameterize them, have them stable if I want to talk about them individually, and then go back. Okay, so it's not necessary that they actually be rational points. They might live in other words, they might live in a finite extension. But it's just convenient to work where they are parameterized. And in fact, if they are, and so let me just follow this theorem up. So the theorem I want to present is in some way sort of generalizing this piece here, and as well as proving that piece of the Mordell-Weil theorem that I didn't complete. And before I do, I want to cite one more piece of the recent history of this discussion. I want to mention this result of Desjardins and Favre, which was published in 2008, to emphasize there's one piece here. This is a statement about stability. So therefore, it was about stability of all the critical points. And then each critical point is therefore has finite orbit, is pre-periodic. But in fact, one can break it apart and treat the critical points independently. And in some work of Romain and Charles Favre, they did that. So I just want to point this out, that they observed that you could do this for each individual critical point. So in this setting, again, the same hypotheses. The statement was that if C is a critical point of my F, again, non-isotrivial, then the statement is that this particular point, just one of them, is stable on the entire parameter space, which I'm calling X star, if and only if that point is pre-periodic for F. Okay? In other words, this if and only if statement holds individually for just one critical point. Okay? And so this is the kind of statement that becomes useful in these discussions about Mordell-Weil theorem and other statements in arithmetic geometry that I was interested in, but not just for critical points, for arbitrary points. So let me now, actually, maybe I'll put this up. and erase this one and state a theorem. And I have, okay, so I know I started at, I guess, 5 after, right? So, okay, so I'll try to just state the theorem and then make some remarks about follow-up questions. Okay, so just the theorem that I wanted to mention is the following statement. So suppose this is our setting. So again, f is a rational function defined over this function field. So it's a family. I want to assume that it's not isotrivial. And I want to assume that P is any rational point, which again, remember, means that it's just a holomorphic map from my parameter space to my dynamical space. Okay. Do I need anything else? No, I think not. So then just to say that the following are equivalent, which the first just being that these are actually, that this point is stable on the largest parameter space that makes sense, where the family has degree d, so on x star, this punctured Riemann surface. Okay. And exactly as in this theorem here, to say that this is equivalent to saying that P is pre-periodic for F. So in other words, as expected, it was certainly expected, it holds for any point. It's not particular to critical points. Unfortunately, the proofs, as they were, depended on the fact that C was critical. So I had to sort of go back and see if it's possible to throw out that hypothesis and require different ingredients. But let me just say, and then the third piece, which is more relevant for the Mordell-Weil part, is that what's called the canonical height here, I'll define it in a second, of the point P is equal to 0. And then, of course, moreover, the finiteness statement. Moreover, maybe I'll say it this way, and then I have to attribute various people for various things. So hold on a second. Moreover, there exists some constant, positive constant, let me call it B, so that the set of all rational points, and I'll write it this way and then explain, for which the canonical height is strictly less than this bound B, is finite. I'll leave that up for the second. Okay. I have just a few minutes left, so. Yeah?
Statement, P can be not anything else. This is not the same P. There exists a B so that...
Oh, yeah, sorry, this is any. No, this is any point, sorry. The entire set of them is finite, yes.
Thank you.
Yeah, sorry, these statements are for our particular point P, just an equivalence, and then it's saying that the collection of all stable points in particular is finite. Yeah. Okay, so height 0, I haven't told you what height is yet, but height 0 corresponds to pre-periodic. So okay, I'll give a definition in a second. It only takes 1 moment to write it down, but I want to give credit where credit is due. So first, let me just remark that, so this equivalence of stable and pre-periodic, okay, so this equivalence here is just the generalization of this statement right here. Okay? And in fact, the only piece of this statement that really required some real work was exactly to show this implication that stability implies pre-periodicity for an arbitrary point P, to throw out that critical point assumption. Okay? Now this equivalence here, the way I've formulated the theorem on the board was already known, in fact, and was proved by Matt Baker, and I even referenced his paper already. So this, and in fact also this finiteness. So in fact the way I've formulated this theorem, this entire piece, so almost the entire theorem, was already known and proved by Matt Baker in this paper that appears in 2008. Okay, so why am I revisiting his theorem? Well, there are 2 reasons why I am actually revisiting his theorem. First of all, the proof is completely different. He's using Berkovich space techniques, which I found sort of hard to really understand. Okay, now I've collaborated with Matt, and we use Berkovich space all the time in our joint work, but I found it very hard to really parse the fundamental idea of what he was doing, so that was sort of led to, of course, redoing it. But there was another piece of it. His method didn't allow for, there was one piece that it didn't give. So in fact, he assumed, as I've written here, that the family is not isotrivial. It turns out one can make a weaker hypothesis, which is to assume that it's not isotrivial over the given field, and still deduce all of these statements. Okay? This just means, so this is a slightly weaker hypothesis. So so in other words, he had a slightly stronger hypothesis in his theorem, and the reason for wanting a weaker hypothesis was in fact to match what was known for elliptic curves. Okay? This statement here includes that finiteness statement that I mentioned for elliptic curves. Okay? That the set of pre-periodic points for any family F is going to be finite, whether it's lattice or not. Okay? So this includes that finiteness statement about torsion points for elliptic curves. Okay? And the way it was known in that context was just assuming not isotrivial over K. Okay? So this just means the complex structure is allowed to be all the same, but there's no Mobius transformation over K that conjugates this to something over C. Okay? I don't know if I want to write that down because I'm basically out of time. And so that said, let me just give a quick definition of this thing because I've written it. Okay? P, remember, is a map from X to P1, and all of its iterates are maps from X to P1. So what is this? This is just the degree growth. This is, if D is the degree of F as a rational function, you take 1 over d to the n, and you just look at the degree of these iterates. That's all that is. There's nothing fancy about this h hat, but it comes from, of course, the Mordell-Weil theorems based on the ideas of Weil introduced to handle the case of number fields, and there's a whole history of these height functions. This is what's called the canonical height function introduced in this context by Call and Silverman. This is what's called the canonical height function. And over a number field, this is easy. Height 0 in pre-periodic is immediate from properties of the height function. But over a function field, it's not true unless the map is isotrivial. And it wasn't known until recently, until Matt, I guess, proved his theorem that this is, in fact, what you get. That isotriviality is the only problem. And so I just needed to strengthen it so that I could have this weaker hypothesis. And I wanted to relate it to stability. So let me finish by emphasizing, so Mordell-Weil was just sort of a cute thing for me that wasn't really my goal to reprove classical theorems. And so I just want to finish by, maybe I'll write it here, by mentioning a motivating question, which is, in full generality, certainly still unanswered. So I want to finish with this sort of sample kind of question which is really the motivation for this statement. Okay? The real motivation for this kind of statement is the following, isn't here, so it's not even the main question. Let me just write a sort of sample question, which is coming from, well, maybe I should say, really posed in its first form by Umberto Zanier, but reformulated in this dynamical context. So really comes from Zanier, which is the following type of question. So again, suppose f is any rational function over a function field. And suppose now I have 2 points, p and q, let's say rational points. And assume, okay, so stable, I'm going to assume they're not stable. So stable here is easy. So the point of this theorem is to say stable is easy. They're just pre-periodic. There are only finitely many. We can throw them away. So in some sense, all of the stuff that I've talked about was to say we can ignore everything that I just said because there are only finitely many. So then we can move on to what's really interesting. So all of this was, step 0. Let me forget about the easy stuff. How do I get to the hard stuff? So assume they're not stable. So they're undergoing bifurcations. So we have bifurcation locus in the parameter space, X. That might be some interesting thing to look at. Okay, remember that this is my field K. So I have some parameter space where I have bifurcations and some chaotic sets, and everything is complicated, and we can do dynamics. Okay, so if I assume it's not stable, then, then one of the consequences of that theorem, for example, is that if you look at the set, of parameters for which P is pre-periodic, for just one of these points, say, if it's not stable, then it's not pre-periodic for all T, but then this set is necessarily infinite, okay? Just like we know for the critical point in complex dynamics. So then this set is infinite. Okay. This is Mordell's theorem. It's not a consequence of the theorem, it's a consequence of the not stability. So I should say maybe assume not pre-periodic, and then it's a consequence of the theorem. So then it's a little more interesting. Assume that it's, that's maybe the other way I should formulate it. Assume that it's not pre-periodic for all T, then I know by the theorem and by Mordell's theorem that this is an infinite set. And so the question was the following, and I'll finish up, sorry, I've gone over and everybody wants to have dinner. The question was, suppose you take 2 points and you know that this intersection is infinite between the 2 infinite sets. What can you conclude about the 2 points? And so really what you want to conclude, and I'll just write it down and then I'll finish, is that, well, if they have infinite overlap, then the 2 sets should be equal. And then furthermore, to take that a little bit further, what can you say? Well, when would it be that these sets where 2 different points are pre-periodic coincide? There should be a reason for it. So this is, of course, also part of the question. There should be a reason, and the reason should be that the 2 points are somehow dynamically related, and I'm not going to tell you what that means, but let's just say heuristically, there's some algebraic relation between the 2 points that explain why you have this overlap. And Zanier, together with Masser, proved a version of this for elliptic curves. Together with Xiaoguang and Hesse Yi, we gave a dynamical proof of this statement, that these kinds of statements are exactly equivalent, exactly when F is the lattice family that I wrote down earlier. But there are other ingredients that I don't have time to talk about. I've already gone over time. But this kind of question is really what was motivating all of this discussion, exactly so then I could say, well, pre-periodic is the same as stable, and we can forget about those points. So, okay, I'm done. I'm sorry.
There's a silly question in the theorem there, the B. You said there exists a B, so that this is finite. Is it not finite for all B? Or?
Yeah. So right. So the difference between in this function field case versus the number field case. So in the number field case, this set would be finite for all B. In this case, it's not. So for example, for the lattice map family, if I take B equals 1/2, so if I have height B equals 1/2, then that set becomes infinite. And because, let me just try to explain, if I take the constant points, the points that are defined over just the complex numbers, and I start iterating them so they don't depend on that parameter t, the computation's dilemma, I didn't have time, I was going to talk about this to give the example. In fact, in that case, the sharp value of B you get is exactly 1/2 just from iterating the constant points. I didn't also mention, I mentioned the z squared plus t family, and I didn't ever come back to it, though I guess I was hoping to, which was in that example, one can compute. So I said this set is finite. What is this set for z squared plus t? Okay. Which points are stable for z squared plus t? Well, no points are stable for z squared plus t except for infinity. Infinity is a rational point, and it's fixed. So it's stable. Infinity is not moving in that family. It's stable. It's pre-periodic. Its degree is always 0. It certainly has height 0. It clearly satisfies these three things. And it turns out it's the only one And every other point has height at least 1/2. So a half, again, is the sharp value for z squared plus t. And unfortunately, the proof does not give an effective bound. It doesn't tell me what that best b should be in general, but it's kind of a fun problem to think about. To like, if you're handed a rational function, what are the actual numbers that you get?
Question about your question.
Yeah.
So now you go to closure, you consider the bifurcation loci associated.
Yes.
And assume that P and Q are not dynamically related.
Yeah.
You have a conjecture how the intersection of bifurcation loci is significantly smaller than the VP and VQ.
Can you say that again? So if they're not?
Assume that this is true. Or
Yeah. And then if I look at the bifurcation locus, right? Yes?
look at the intersection between the two when the two guys are not.
Can you say something about this thing being?
This is smaller than the two bifurcation loci.
I don't know how to say anything there. So by analogy with, say, the Julia set pictures. So we know that, so there are certainly Julia sets where the sets themselves have a lot of overlap. For example, if I take real C, real and negative, and I take various choices where the Julia set contains an entire interval in the real line, then I can set it up so there are no, say, pre-periodic points in common at all, no algebraic relation, but lots of overlap with the Julia set. So what I would expect is that a similar thing can happen here. That even if P and Q are not related, so even if this intersection is in fact empty, that maybe the intersection of the bifurcation loci for the points could be really big. I don't know. I've never seen this, but I don't know how to do explicit examples. But I've seen, I guess I do know explicit examples, I should say. Even with critical points. So even when these are actual bifurcation loci, and this is critical point 1 and critical point 2, I expect that they're never going to be exactly equal. But there are certain examples that I guess I played around with computationally where the two critical point loci, I know that they're not dynamically related, but the bifurcation loci look essentially identical. I forgot that, in fact, if you take, and I'll mention just for fun, let me just mention this explicit example. If you take the map, sorry, Scott and Joanna and Dan, I know you guys know this formula, yes, I've just blanked on which one it is. It's negative 4z plus tz plus 1. Thank you. Okay, so this is pier 1 of minus 4. Okay, sorry, thanks. So I know they've been playing around with this. So if you look at the bifurcation locus for this family, the actual bifurcation locus in the usual sense, there are two critical points. So there's sort of two bifurcation loci to look at. They look like they're equal. But I know we can prove that the two critical points are independent. So this does not happen, but the bifurcation loci look nearly equal. But if you zoom way in, you see that they're not. Yeah, minus 4 seems to be. Well, that's exactly what these guys are working on. In fact, some way they're right now doing numerical stuff to try to say why the bifurcation loci overlap might happen for this family more than others. Right? I think.
Right.
Yeah, there you are.
Questions? Okay, let's thank the speaker again.